Hi everyone, welcome to my video on volumes of revolution. This comes into Core 3 Mathematics in the OCR board, and it's quite an interesting topic because it's going from areas to volumes, okay? And the way we do that is we think about any old graph, okay? And what we do is we either spin it around the y-axis to get a volume, or we spin it around the x-axis to get a volume. And I'll try and draw it into 3D. You'd get a solid bullet type shape from that red curve. Okay. Now I want to use this to show you how to find different formulas. So I'm assuming that you have already seen volumes of revolution and you know the formula for it. If you're spinning around the y-axis, your formula is going to be pi times the integral between your two limits of x squared with respect to y. If you're spinning around the x-axis, it's going to be pi times the integral between your two limits of y squared with respect to x. And we substitute in a formula for y or a formula for x. Okay, so what we're going to do is we're going to start off with some basic 3D shapes that you probably already know the formula for, but I want to show you different ways to generate it. So I've drawn a cylinder, okay, and to know the formula for the volume of a cylinder, you need the radius of the circle R, and you need the height of the cylinder. Right, what I'm going to do is I'm going to take this shape, and I prefer to spin around the x-axis, so what I'm going to do is I'm going to put it how we're going to generate it. So we're going to put it on its side, and that is how we're going to spin it around. Now you've got to be quite good at visualizing things to be able to do volumes of revolution. You need to think, to get a formula, what do we rotate around the center to get a cylinder? And if you have a think about that, the answer is all you need is a rectangle. When you spin that rectangle around, it will go into a cylinder. Okay, so we're going to draw on our rectangle. Remember, our aim is to come up with formulas. So for that reason, we're not using any numbers in particular. We're using a general R to represent the area, and a general H, which is now on its side, to represent the height. So comparing to our drawing, this is going to be R, this is going to be H. Okay. Now what we need to think about is what line are we talking about? What line are we thinking about when we first off integrate to find the area below and then spin it around? Okay. The answer is quite simple, really. If you've gone from 0, R up, you're at R, and every single point on this line, y equals R. So it's a very, very simple formula in this case. Our limits, well, we want to integrate between 0 and all the way up to H. We've gone from 0 across H, we're at H, okay? So let's set up our formula here. So it's pi. You might have seen pi inside the integral. Because pi is a constant, you can just take it outside. That's all I'm doing there, just to clear that up for you. Between 0 and H, and our formula is y squared. Now in our case, y equals R, so y squared is R squared. We're integrating with respect to x. Okay? So what we're going to get is we're going to get pi. Let's integrate R squared. This confuses some people, but if you understand integration, it will not. We are integrating with respect to x. R is not a variable. R is a constant. We've just not defined what it is yet, okay? R takes constant values. It's our radius once we've defined our shape, okay? So this is a constant. You can think of it as maybe a letter A. You're integrating a constant with respect to x. You're going to get, if it was a, you'd get ax. If it's r squared, you're going to get r squared x. Okay, think about that for a bit until you get your head around what's going on. I'm sure if I asked you to integrate 5 with respect to x, you'd know that was 5x. Same principle applies. It's just we don't know what r is in this case yet. Right, now we integrate between the limits. Okay, biggest one first, which is h. So we substitute in for x. R is constant. It stays how it is. So we're going to get r squared times h. And guess what? That's your formula straight off for you there. Okay, so the volume equals pi r squared h. And like I said, you might already know that one, because all you're doing in terms of normal maths is finding the area times in by the height. Okay, cross-sectional area pi r squared. So it's really, really cool that we can come up with a formula that you've seen probably before using basic maths, and we've done it by integration, which is calculus, and it's very, very cool that we can do that, I think, anyway. Right, next shape we're going to look at is the cone. Let me try and draw a cone for you. We're going to try and think of the volume of this cone. So we're going to have to spin around, okay? Now, like I've told you already, I like to spin it around the x-axis. So this is how I'm setting up my cone, okay? So we can spin around like that. So we need to think, when we've got a cone, what things do we need in the formula? Well, it's easier to see when it's upright what you need, so I'll draw it again. You need the height of the cone, which is the vertical height, making a right angle there, and you need the radius. Okay, so similar to the cylinder that we've just done. Let's set up our axis. This one's harder to get the equation of, but I'm sure we will manage it. Do not worry about that. Okay, can you see that if we rotate this triangle around, we're going to get the cone shape we want? Remember, we're keeping it general so that we can come up with a cool formula, okay, for any r and for any h. This bit is actually your radius. Can you see? That's your radius there. So this is up r, and as I said before, that length is r. I'll draw a dotted line so you can see what I'm getting at. The other one across is your height. We've got it on its side here. Okay, so again, that length is h. Going from 0 is going to mean that we've got h here. Now we're on to the job of applying our formula. So it's going to be the integral pi between our limits are 0 and h of y squared. We've not got a formula yet for y. So let's think about what we know. The key things we know about this green line are it goes through the origin. So think of y equals mx plus c. It's going through the origin, that's going to be 0. So it's going to be y times the gradient. Y equals the gradient times x. So all we need is gradient. Remember, back to basics, gradient means how steep a line is. Okay? And you might have heard change of y over change in x. Well, we know that the change of y over the whole triangle is r, and the change in x is h. Okay, so that is just r over h. So we've got our equation, y equals r over h times x. How good's that? In our formula, remember though, we need to square it. Okay, so we're going to take y and we're going to square it. And we're going to integrate with respect to x. And this time we've got an x involved. Right, let's just simplify before we integrate. Going between 0 and h. Square everything in this bracket. So it's r squared over h squared. I hope you're shouting at the screen now that r squared and h squared are just constant. They're very different to this x, which is the variable that we're integrating with respect to. R and h definitely do not depend on x. Okay, so what we need to do now is we need to integrate. So pretend that's a constant. Well, it is a constant. Let's integrate it as if it was just the letter a, for example. Okay, So a times x squared, add 1 to the power of x, divide by the new power. So the new power is going to be 3, so it's a third, r squared over h squared times by x to the power 3. And we are integrating between 0 and h. Right, so let's get on with it then. Okay, subbing in h as x as our biggest value, we're going to get a third r squared over h squared times h cubed, and the 0 again in here just cancels it out. Okay, so all we need to do now is simplify. We've got h over h squared, which is just going to leave you with h, and hence you've got a third pi r squared times h as your volume. Okay, you might recognize that for the formula for the volume of a cone. How cool is that? Right, next one we're going to look at is a sphere. Getting a little bit more difficult and a little bit more difficult for me to draw, I'm afraid. So yeah, it looks like a circle, but let's try and make it 3D using some art skills. But if failing that, let's just try and show it's 3D. Okay, so it's a 3D ball sphere. Now it's quite tricky to think about how you're going to spin a line around and get that. Okay, after a bit of thought, you might start thinking of spinning that around or spinning this around. Okay, what I'm going to do is I'm going to think, well, a sphere is symmetrical, so my plan is to find the volume of a hemisphere, just the top of it, okay, and then we're going to times by 2. Don't let me forget times by 2 at the end. So let's draw that again because it's not very straight. We're going to center things around the origin, because if you remember from core 1 or core 2, from coordinate geometry, you're going to have x minus a squared plus y minus b squared equals r squared, where r is the radius, okay, and the center is AB. Now if we make the center 0, we don't need these things anymore, okay, which will make our formula nice and simple, which is what we want in maths. So let's draw it on. That is a quarter of our circle, and it goes up by the radius r and across by the radius r. Think about equations of a circle. I've just basically told you the centre's 0, so 0's there, 0's there. The equation of this is y squared, x squared plus y squared, doesn't matter which way around. I'm already a bit step ahead, trying to simplify, make y the subject. So let's take away x squared so that we get y squared equals r squared minus x squared. At this point you could square root. Okay, if you were to square root, you would not need to do the plus or minus because we do not need this side. Okay, so we do not want the minus version, we just want the positive. So what we're going to do is we're going to sub that straight in to our formula. The volume, V, pi times the integral between our limits, which is 0 and r. We're going to spin it around this way, okay, because I just think it's more conventional. And we're going to be integrating r squared minus x squared. Remember, y squared from the formula with respect to x. R is a constant, x is what we're integrating with respect to. Okay, so they look very similar, but they're very different. So let's integrate r squared. It's a constant. When we integrate, we're going to introduce x, r squared x. When we integrate x squared, we get x cubed over 3. And we're going between r and 0. Right, let's just simplify and substitute in here. When we sub in r, we're going to get r squared times r, which is r cubed for the first term, and r cubed over 3 for the second term. Again, when we substitute in 0, we're going to get 0 and 0 again. Okay, quite boring. So, here we've got a whole r cubed, take away a third r cubed. So 3/3 r cubed, take away a third r cubed is going to give us 2 pi r cubed over 3. Okay, 2 pi r cubed over 3. Now, remember I told you to shout at the screen? That's a hemisphere, that's half of your volume. Okay, so what we need to do is we need to do 2 times, 2 times, 2 times, 2 times. So actually, it might be, you already know the formula, 4 pi r cubed over 3. Okay, that's right. Right, I did want to show you 2 more, but to be honest, I'm a little bit nervous about the last one I wanted to show you. Give you a sneak peek, bit of a spoiler. I was thinking about spinning that around this axis, okay? But I've started to look at it already, and I'm getting a little bit confused with the maths. Before we do that, what I want us to look at is a rugby ball, okay? Now, we can think of a rugby ball as an object that's been rotated around. Okay, span around, you get yourself a rugby ball. So you can think, well, we're just in a football, just in a sphere, so it's only fair now if we do a rugby ball. Okay, I didn't actually know much about this shape until yesterday, and apparently it's called a prolate spheroid. But to be honest, I did not know that. Okay, so what we're going to do is we're going to try and make this rugby ball shape. I'm just going to keep calling it a rugby ball, to be honest. You know what I mean. Right, so just like the sphere, we can be thinking, right, so, okay, we could go about that area, but what it's nicer to do in terms of the integration, making things simpler, is to think of a quarter. Okay, so what we're actually going to do is we're going to find half of the rugby ball. In particular, from the diagram, this half. So again, remind me at the end, we need to times by 2. Right, so you're probably thinking, what on earth? How do we even get that line? What is going on with that equation? Well, I'll tell you what's going on with that equation. We started off with a circle, and we've applied a stretch of a certain scale factor across, and a stretch of a certain scale factor up. So it's no longer a circle, okay? In 2D, it would be an ellipse. And it doesn't really make sense to talk about a radius anymore because it's not, radius is just for a circle where it's the same all the time. Now it's going to be different. Can you see? Different here to here, for example. Now, in terms of the maths, we say that we're going to be stretching it across by the constant A. Okay, so we're going to be stretching it across by a constant A. So that goes to A. And we're going to be stretching it up by a constant B. Now, if you really understand your transformations, thinking about the circle around the origin, x squared plus y squared equals r squared. Remember, it doesn't make sense to talk about the radius anymore, so we'll leave that for a second. You will understand that what we're actually doing is we're doing x over a all squared, because we're transforming x stretched by a. I hope that makes sense from your transformation lessons. And we're doing y over b. This is going up to b, by the way, all squared. And that can just equal 1. Okay, and that's going to work out. So let's get down to some business. Let's apply our formula. Pi times, and we're going to integrate between 0 and a. We're going to spin around this way again. Okay, and we're going to be integrating y squared. So what we need to do is we need to rearrange our formula to get y squared equals. Okay, well, wondering how much space I'm going to have here. Y over b all squared, that's y squared over b squared. We're going to take this away from both sides. So we get y squared over b squared, in 2 steps, I guess, equals 1 minus x over a all squared. Okay, and now we're going to times it by this b squared here. So times up both sides by b squared. This is what we're going to have to integrate. Okay, doesn't look very nice, but do not worry, it will be, because just remember a and b are constants. 1 minus x over a all squared. Okay, with respect to x. Sorry if that's getting a little bit messy. Right, b squared's a constant, so it can wait outside until we're finished. Okay, and we're trying to integrate 1 minus x squared over a squared. Okay, or you might want to think of that as the constant 1 over a squared times x squared. Same thing. One is a bit easier to see what's going on than the other, that's all. Right, now we're actually going to integrate. Integral of 1 goes to x. Integral of this thing, okay, the second term, we're going to be treating 1 over a squared as a constant because it is. X squared, well, we're going to make the power 3 and divide by 3. So it's going to be minus a third 1 over a squared x to the power 3. And the limits we're going between is a and 0. Okay, so pi b squared still waiting patiently outside. What we're doing is we're substituting in x for our biggest value of a. So it's going to be a minus a third 1 over a squared times by a cubed. Look how nice this is going to be, because we're going to have a, and a squared times a cubed, 1 over a squared times a cubed just goes to a. So it looks similar to before, because it's a similar shape, isn't it? Okay, you've got 1a minus a third a. That's going to go to 2 thirds a. So when we simplify that, we're going to do 2 thirds, we'll put it at the front, pi a b squared. Remember, I'm glad I didn't forget, that's for half of the area we're interested in. So let's go back and cheat. Put times 2 next to everything. Okay, so instead of being a 2, again, similar to a sphere, it's going to be 4. That's the volume. Now, usually I answer questions in my videos. I show you how to do things, but I'll be honest with you. I've been looking at this torus, and it's been confusing me. So, what do I mean, torus? Well, when we spin around the center, we just get 0. That's fine. We just get sphere. But what about when we start spinning around, and we've translated our circle across here? It starts getting tricky. Okay, it starts getting very, very tricky. Now, I'm going to tell you a bit about what shape we're going to get. If we spin around here, can you think about what's going to happen? This circle is spinning around. It's in 2D, so it might not be very clear. Spinning around, blah, blah, blah. Okay, have you got good visual awareness? Are you good at visualizing things? Can you think what's going to happen? I'll give you a clue. Think about Homer Simpson. What's actually going to happen is this is going to spin around, and it's going to make a donut shape. And in maths, we call the donut shape torus. So this donut is quite hard to draw, to be fair. Okay. You're probably better at drawing that than me. So that's supposed to be our donut. And it's made from spinning that circle around the center. Now, to the maths. Two defining things of a torus are where, obviously the radius of this circle, we call that r, but actually as well, the radius of the circle from the center that is spun around. So imagine that this circle is on a stick, and we're spinning that stick around from this pole. Okay, if you've got a weird imagination like me, that's going to give us a donut shape, a torus. Now I'm just going to give you a starting point, and maybe someone who's better at maths than me can give me a hand this time, because I've looked at what the formula should be and I can't quite get to it. I got myself into a tricky integration problem. So I'm just going to help you set this up. So y-axis, x-axis, and then I'm going to leave you in the lurch, to be honest. It's way above core 3 anyway, so do not worry about that. I'd just like to show you some extra things. Remember we said we're spinning it around here, so this is at r, and this is our radius, so this is going to be r minus r. This is going to be r plus r. Right, so in terms of the formula for the circle, remember what we said about x minus the x-coordinate of the centre. The x-coordinate of the centre is now r, plus y minus the y-coordinate of the centre is just 0, so that's fine, equals the radius squared. So we've got our r involved, and we've got our radius involved. We've got both radiuses we need. Now, what we're going to be doing is we're spinning around the y-axis. So we actually want x equals. And this is what has been confusing me. Okay? So when we rearrange this, we're going to get r squared. Now I won't try and do it all in one go, obviously. Let's do it one step at a time. So we're going to get r squared minus y squared. We're going to square root, and my plan was to just spin around. Actually, could I just do, I think I might have looked at that as well. We're going to try and spin around this or the whole thing there. But either way, we're going to just find half our donut. Imagine your bagel in the morning. You want to put it in the toaster. Donut shape, cut it in half. Half goes in one side of the toaster, half in the other side. So, cut long story short, we don't want a negative version when we square root here. Okay, that's all I was explaining. Square root of r squared minus y squared. Okay, and then we add r. Now it'd be so much simpler if that r wasn't there. Make life very easy. But it is there. We can't avoid it. So when we set it up into the formula, in my opinion, we would be integrating between r minus little r, big R, plus little r. And it's going to be this squared, x squared. Now, this is where I've become unstuck, okay? I wanted to show it you, okay, granted, you've not got all the answers in life that you wanted, but there you go. So, this is where I'm up to. Yes, I've expanded this out and managed to integrate most of it, but we get a term that is 2r root r squared minus y squared, which I think is very difficult to integrate. I'll leave you there, okay? I'll leave the video there. I hope the rest of it's been useful. We've managed to do a half of a donut shape, kind of, but we managed to do a rugby ball, managed to do a sphere, a cone, and a cylinder. Hope it's been useful, guys. And if you have some ideas on the last one, give me a shout. I'm willing to think about what you think. Right, thanks for watching, and achieve maths.